Hey kids, this is day 2 of chemical reactions. We're going to be predicting products of a couple of new reactions and learn how to write those reactions. So let's get started. First type of reaction that we're going to learn today is called a single replacement reaction. A single replacement reaction is one in which an element reacts with a compound to form another element in compound. One element actually takes the place of another element as part of a compound. A metal will replace a metal and a nonmetal will replace a nonmetal. The general form is down here. So if you have a single element A and a compound BC, if A is strong enough, it will replace B in this compound. And so B doesn't go away as you see in the products. It's simply a new product by itself. And then A takes the place of B to form the compound AC. Here's a couple of examples. We have iron by itself plus copper nitrate. Okay, so if iron is strong enough, it is going to kick copper out of that reaction and replace it. Over here, copper's by itself and iron nitrate is the new compound. So how do we know if it's going to be able to do that? Well, we use something called the activity series, and here it is. An activity series, which is somewhere in your notes, it's in your notes. The activity series shows elements in order of their activity or their reactivity. You'll find the first element on your list, iron. So you look in your list and you go, okay, where's iron? Okay, there's iron. Then you find the element it's trying to replace. Well, iron is a metal, so it can only replace another metal, which is copper. So you find copper. So there's iron. Copper is right there. So what that means is that iron is stronger than copper. So iron can replace copper in the reaction. That's why iron is able to kick copper out and form the new compound iron nitrate, and copper is just by itself now. Again, it doesn't go away, it doesn't disappear, it's simply a single atom by itself. The next reaction, fluorine is a nonmetal. Well, we have some nonmetals here. Remember, nonmetals can only replace other nonmetals. So in this reaction, fluorine is going to try to replace bromine. Because fluorine is a nonmetal, potassium's a metal. It can't replace potassium. Can replace bromine. So you look on your activity series. Well, here's fluorine and here's bromine. So what that means is fluorine is stronger than bromine, and fluorine will be able to kick bromine out and form the new compound potassium fluoride. It will bond with potassium, and then bromine will be left by itself. The activity series. So a little about this activity series. Not all single replacement reactions can take place. The reaction will only take place if the single metal or the nonmetal is more reactive than the metal or nonmetal it's trying to replace. And we use the activity series for metals and nonmetals to determine this. So if the element that's trying to do the replacing is higher on the activity series than the one it's trying to replace, it will be able to replace it. However, if it's trying to replace, let's say chromium is in a reaction, it's trying to replace calcium. Chromium is lower on the activity series than calcium, so that means chromium cannot replace calcium. Chromium cannot replace anything above it, but it can replace anything below it. Okay, so that's the way that the activity series works. Here's a copy of the activity series. You are welcome to print this page if you need to. Our example here, chlorine gas is bubbled through a solution of potassium bromide. So what would that reaction look like? Well, chlorine gas is Cl2. Okay, chlorine gas is bubbled through, so that means I'm adding it. Is added to a solution of potassium bromide. The symbol for potassium is K. The symbol for bromine is Br. Potassium's oxidation number is +1. Bromine is -1, so I don't need any subscripts. Remember that chlorine is diatomic, so that means it can't exist alone. It always has to be bonded to itself if it's by itself. And remember those diatomic molecules, the Brinkelhoff atoms, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. All of these atoms, when they're singles, they'll be bonded to themselves. So they'll exist as Br2, or in this case, Cl2. Okay, so chlorine is going to try to replace either potassium or bromine in this reaction. Which one do you think it'll replace? Chlorine is going to try to replace bromine because chlorine is a gas, so it's only going to try to replace another gas or nonmetal. So I go over here to my activity series. Well, here's chlorine and here's bromine. Can chlorine replace bromine? Yes, it can. So it'll kick bromine out, so bromine will be by itself. But remember, it's diatomic, so when it's by itself, it gets a subscript of 2 plus potassium chloride. Potassium's oxidation number is +1, chlorine is -1, so I don't need any subscripts there. Okay, I do need to balance this reaction. Okay, I need to do that. So 2 chlorines here, 1 chlorine here. So I'm going to use a coefficient of 2 to balance those chlorines. Well, now my potassium is unbalanced. I have 2 in the product, but only 1 in the reactant. So I use a coefficient of 2 to balance those potassiums. Then my bromines are equal. So that's how you use that activity series. Chlorine can replace bromine in that compound and bromine is produced. Replacement reactions are not reversible. The reverse of the reaction could not take place because bromine could not replace chlorine. See? Bromine cannot replace chlorine. So that's why the reactions for these single replacement reactions are not reversible. Why doesn't the reaction go in reverse? Again, chlorine and bromine are both halogens. A halogen can only replace a halogen below it on the periodic table. Chlorine can replace bromine and iodine, but it cannot replace fluorine. Metals undergo replacement reactions based on their activity. So let's predict the products of these reactions. Okay? That first reaction. Here, I'll keep your activity series handy right here. That first reaction. Iron is going to try to replace another metal. What's it going to try to replace? Magnesium. It's going to try to replace magnesium. So the question is, can iron replace magnesium? Well, let's find them both on your activity series. There's magnesium and there's iron. So can iron replace magnesium? No, it cannot. So that reaction will not happen. In reaction B, iron, here's iron again, is going to try to replace copper because they're both metals. So can iron replace copper? It sure can. It sure can. So iron will replace copper and form iron sulfate, and copper will just be a single atom by itself. Potassium chloride plus bromine. So what is that single bromine going to try to replace? It's going to try to replace chlorine. Can it? No, bromine cannot replace chlorine. So look, iron's going to try to replace magnesium. Can't do it. No reaction. Iron can replace copper. We looked. We found that. That's going to work. So copper plus iron sulfate is my new my product. Okay. Copper does not get a subscript of 2. Only the Brinkelhoff atoms do. Copper is not one of these. Okay, so that last one that we looked at, could bromine replace chlorine in that reaction? Nope, sure can't. No reaction. And we love those. Those are easy. Okay, so on to double replacement reactions. Double replacement reactions are when a metal is present in 2 compounds and they change places and they form 2 new compounds. All they're doing is switching partners, like when you were little and you had to square dance. You know, you're just switching partners. You're still doing the dance, just switching partners. A metal will always replace a metal, and a nonmetal will always replace a nonmetal. Okay, we begin with 2 compounds, a cation and an anion. So we've got an ionic compound, and we end with 2 different compounds. Down here is the way the reaction will look. See these metals, the places where they are, AX plus BY? Well, A and B just switch places. So you'll have BX plus AY. Okay, so here's some examples. Sodium fluoride, right here, is an ionic compound, and it's being combined with potassium bromide. So what's going to happen is that sodium and potassium are simply going to switch partners. So the new compound will be potassium fluoride, because potassium bonds with fluorine, and sodium bromide, because sodium will bond with bromine. It's just switching places. A longer reaction does not mean it's more complicated. Barium and sodium are going to swap partners, and you'll get barium sulfate over there and sodium nitrate right there. So we're going to predict the products of this reaction. Let's see. I've got it right here. Iron 2 nitrate in solution reacts with potassium oxide in solution. So let's go ahead and write that reaction. Iron 2 nitrate. So iron is Fe. That 2 means that it has a +2 oxidation number. Nitrate is NO3, and it has an oxidation number of -1. So those are going to be crisscrossed for my first formula. FeNO3, 2. It's in solution and it reacts with, so that's, I'm adding that. I'm adding what? I'm adding potassium oxide. So potassium is K. Its oxidation number is +1. Oxygen's oxidation number is -2. So you crisscross those and use them as subscripts, and the formula is K2O. So in this double replacement reaction, you have two compounds. They're going to swap partners. That's it. Okay? So my new compound is going to be iron bonded to oxygen. Iron's oxidation number was +2 and oxygen's is -2, so I don't need any subscripts. The other compound is going to be potassium nitrate. Okay, they swapped partners. Potassium's oxidation number is +1, nitrate's -1, so I don't need any subscripts here. I do, however, need to finish off by balancing the equation. I have 2 potassiums here, 1 here. So I can add a coefficient. So 2 potassiums, 2 potassiums. 2 nitrates, and look, that works out for us. 2 nitrates. Just as with single replacement reactions, not all double replacement reactions will occur. We investigate precipitation reactions and solubility rules now to see how they impact the predicted products. Okay, how do we know that a chemical reaction has taken place? Okay, well there's several ways. This is just a few. There may be a color change. There may be a gas or a solid precipitate. That's what we're going to work with now. A solid precipitate formed. There may be an energy change, meaning that the reaction would be hot or it would be cold. There may be a new odor or a change in odor. The chemical equation is a way to represent chemical reactions on paper. Just a reminder that reactants are on the left, products are on the right. So we have a couple of examples here, and we've got the balanced equation. So when you predict products of double replacement reactions, you're going to write the switched combination. So we've done that up here of the metal and the nonmetals. We've swapped partners. Then you're going to use your solubility rules, is what it should say, your solubility rules, to determine if any of these combinations are soluble. If only soluble products are formed, then a double replacement reaction is said to not occur. We are looking for a precipitate in the product. Okay? That's what this is talking about. If at least one insoluble product is formed, otherwise known as a precipitate, then a double replacement reaction is said to occur. We are looking for something magical to happen. We're looking for a solid to be produced. Here's some solubility rules that I'm hoping you're going to memorize. You can use them on your test, though. So they're just the basics. They're a lot more complicated than this, but these are the basics. Things that are soluble. Anything in group 1, any of the alkali metals in the compound, if there's an alkali metal, it's soluble. That means it will dissolve. Ammonium ions, NH3 ions, those are soluble also. Also soluble, anything that has a nitrate, acetate, chlorate, or a cyanide. Those are soluble. Okay, they will not form a solid product. Also soluble, all binary, remember that's 2 elements, binary compounds of chlorine, bromine, and iodine. So sodium chloride, calcium chloride, potassium bromide, those things would be soluble. The exception to this is if chlorine, bromine, or iodine is bonded to silver, mercury, or lead. These guys are bad actors. So silver chloride, insoluble. Mercury iodide, insoluble. Lead bromide, insoluble. Okay, those are our exceptions. Now, the things that are insoluble that you can count on. carbonates, anything that ends with a carbonate, phosphate, chromate, or a dichromate, unless they are with this first rule, unless they're with an alkali metal or ammonium. Okay? So we have iron chloride plus potassium sulfide. Okay? Iron chloride is going to swap partners with potassium sulfide. We're going to switch the iron and the potassium. Okay? And we'll get potassium chloride plus iron sulfide. So iron sulfide forms a solid product. Okay? Potassium chloride is aqueous. Remember that anything that's group 1 it's aqueous. That means it's going to dissolve into its ions. Okay? Iron sulfide will form a solid product. So let's do this particular reaction, or these reactions. We have some solubility rules that we can use also. So here's a copy of the other solubility rules that we use. They're here in the middle on this periodic table. You can use basically any solubility rules. We'll have a copy of the solubility rules uploaded for you though. So here are the solubility rules we're going to refer to. Notice that at the top in this section, we have all of the things that are soluble in water. So there's ammonium. There are no exceptions to these. So if something ends in acetate, it's always soluble. Nitrates, always soluble. Here's our bad actors, silver, lead, and mercury, okay, bonded to bromine, chlorine, or iodine. But if it's not silver, lead, or mercury, bromine, chlorine, and iodine compounds will be soluble in water. So the insolubles are at the bottom. Here we have the compounds that are insoluble. Now, their exceptions are over here. So carbonates are insoluble unless it's ammonium carbonate or any of the group 1 alkali metal carbonates, you know, like sodium carbonate. That would be soluble. So here's our sulfides at the bottom. Sulfides tend to be insoluble, meaning that they'll form a precipitate unless they're combined with ammonium or a group 1 alkali metal. Or, we have a couple more exceptions here, calcium, strontium, or barium. Okay, these take a little bit of work getting used to, but you can do it. You can definitely do it. I'll show you how. All right, so for this first reaction, we're going to go ahead and predict the products. So zinc and strontium are going to switch places. I will have zinc chloride. Okay, zinc's +2, chlorine's -1, so it'll be ZnCl2 plus strontium sulfate, SrSO3. Oh, so far, sorry, 4. I thought it was sulfite. Okay, strontium's +2, sulfate's -2. So now that we've done this, we need to make sure that it's balanced, and it actually is. 1 zinc, 1 zinc, 1 sulfate, 1 sulfate, 1 strontium, 1 strontium, 2 chlorines, 2 chlorines. So now we need to see if our products are soluble or they're insoluble. Are they aqueous? Aqueous means that they're soluble, they'll dissolve in water. Or are they solid products? Okay, well let's go back and look at our list. Okay, zinc chloride first. Okay, so we find the chlorides. Here's the chlorides. Chlorides are soluble. That means they're aqueous, unless they're silver, lead, or mercury. Is that silver, lead, or mercury? No. So you put an AQ next to it because it's aqueous. It will dissolve in water. Next compound, strontium sulfate. Well, let's find sulfates. Sulfates right here. Sulfates are soluble. That means they'll be aqueous. They'll dissolve in water unless they're with strontium, barium, lead, or mercury. That's strontium sulfate. That's an exception. So that is our magical solid product based on the solubility rules. All right, next compound. Let's see, let me get that in there for you. Aluminum iodide. So aluminum is Al, iodine, I. Aluminum has an oxidation number of +3, iodine's -1. So it'll be Al I3 plus calcium carbonate. Calcium is Ca, carbonate CO3. Calcium's oxidation number is +2 because it's in group 2. Carbonate is -2. So we're going to swap partners here. Aluminum and calcium are going to switch partners. So my new compounds will be aluminum carbonate. Aluminum's oxidation number is +3, carbonate's -2, so I would switch those. 2 there and a 3 there. Plus calcium iodide. Calcium's +2, iodine's -1, so it'll be CaI2. All right, so let's balance the equation. There's 2 aluminums here and only 1 here. So let's see if that'll work out for us. Put a 2 there. That gives me 6 iodines. So let's go over here and fix that. 3 times 2 would give me 6 iodines. Well, that means that I have 3 calciums. So I put a 3 right here. 3 calciums. 3 carbonates. 3 carbonates. So my equation's balanced. Now I look up the products and see if they're aqueous or if they're solid. First one I look up, aluminum carbonate. Okay, carbonates are down here. Carbonates are solids. They form solid products. Carbonates form solid products unless they're with ammonium or a group 1 metal. Well, that's not ammonium and that's not a group 1 metal. So that is our solid product. Let's check calcium iodide just to be sure. The iodide's right here. They're soluble, so that means they're going to be aqueous unless they're bonded to silver, lead, or mercury. Okay, that's none of those. So you give it an AQ because it dissolves in water. Okay, that last little reaction there. Barium bromide plus sulfuric acid. So barium is Ba, bromine. Barium is +2, oxidation number. Bromine has -1. So you crisscross those and you get BaBr2. Plus sulfuric acid. Okay, sulfuric came from sulfate. Remember I ate something icky. So if it's ick on the end, it came from an ATE polyatomic ion. So acids begin with the letter H with a hydrogen. Okay, and that came from sulfate. That polyatomic ion is going to be sulfate, SO4. Hydrogen's oxidation number is +1, sulfate is -2, so you'd crisscross those. H2SO4 is the formula. So now that we have those, we need to swap partners. Swap those positive ions. Yeah, I know hydrogen's not a metal, but they're both positive. So we're going to swap the positive ions. And I will get Ba, barium, bonding with sulfate, plus H bonding with Br, hydrobromic acid. Barium's oxidation number is +2, sulfate's -2. No subscripts are needed there. Hydrogen's +1, and bromine's is -1. So I don't need any subscripts there, but I do need to balance the equation, which actually is going to be pretty easy. I have 2 hydrogens and 2 bromines. All I need to do is put a coefficient of 2 there, and that'll give me a balanced equation. So let's check barium sulfate. Sulfates are right here. Get that off. Sulfates are right here. It says that they're soluble, so they're aqueous, unless they're bonded to strontium, barium, lead, or mercury. Well, that's barium sulfate, so that means that is our solid product. Okay, HBr. Let's check the bromines. There's bromine. Bromine is going to be aqueous also, unless it's bonded to silver, lead, or mercury. Well, it's not. So that's my aqueous product. Okay? If you had trouble with those and the solubility rules, rewind it. Rewind it and go back over it again. Okay? Okay. This is where we're going to stop for today. And I hope you guys are doing okay with it. And if you have any questions, be sure to email and see if we can't get together in a Canvas conference.